Okay, continuing with where we left in the previous video, we were discussing the loads for bridge design, the permanent load and the transient loads. We discussed the permanent loads, the dead load of concrete, including the structural and non-structural components, and the dead load of bituminous wearing cores. Now the transient loads. The gravity, especially the live loads due to vehicular, railway and pedestrian traffic is transient loads. Okay, the automobile is one of the most common vehicular live load on most bridges. It is a truck that provides the critical load effects in case of bridges. Neutral loads due to water, wind, earthquake and ship collisions are also the transient loads. So these are different types of transient loads. Okay, further elaborating the transit loads, it says that following effects caused by live load are also very important and must be considered in the design of a bridge. This includes the impact, uh, its dynamic effects, for example, the impact of a big, uh, you can say the impact from a big boulder, like a piece of rock, to the pier, or impact from a truck, or impact from any kind of the moving mass. So it will have some dynamic effects on the bridge, depending on which element of a bridge is it hitting, with what speed and what is the mass. The second thing is the braking forces. Again, it depends on if a truck, for example, a big truck moving with the speed of, let's say, 80 miles per hour, and it applies sudden brakes. So the force will be much huge in magnitude. Okay, a large force will apply. Similarly, centrifugal forces, in curves, there are centrifugal forces. So again, depending on the magnitude of the force, it depends on the mass of the object, the moving object, and the effect of other trucks simultaneously present. For example, if there are more than one truck present on the bridge, so what will be their effect, combined effect, or the mutual effect? While talking about the vehicular design loads, the Ashton design loads model consists of three distinctly different loads, which are design truck, design tandem, and design lane. So now we are coming towards the design of the bridge, which includes the analysis and design simultaneously. So three different types of loading are there, which is considered by the ASHTO. Okay. The vehicle combination as described in ASHTO 1994 LRFD bridge specifications are designated as HL93 for highway loading accepted in 1993. So in United States, they unanimously selected a truck designated as HL93. Why 93? Because it was accepted as a highway loading in 1993, and in the next year, 1994, OSHTO just take it as a standard vehicle for designing the bridges. What is the HL93? We will see on the later slides. Okay, so this is basically the HL93 truck load. You can see that it has three axles. Okay, the front axle, it has a load of 8 kips, and the middle one and the rear one has a load of 32 kips each. The dimensions are the distance between the front axle and the middle axle is 14 feet, and the distance between these two rear axles, the middle one and the last one, it varies from 14 feet to 30 feet. Okay, so it could be 14 feet, 20 feet, 25 feet, or 30 feet, the distance between these two axles, right? Talking about the transverse direction, this was a longitudinal direction. In transverse direction, the distance between the tires, the center to center distance is 6 feet. However, the clear distance from the center of one tire uh, to the distance to the next tire should be 24 inch, which is 12 sorry 2 feet. So this distance should be 2 feet general, right? So the design lane calculated on the basis of these things is about 12 feet. So the design lane should be 12 feet in width, right? Coming to the simplified form, for example, if this is a girder of a bridge and the truck is moving along its length, so if it is entering from this side and the truck is moving on, and right here a complete truck is on the girder. Now you can see that the 8 caves, 32 caves, 32 caves loads are applied at a distance specified in HL93. So you can analyze this girder considering it as a beam, and you can analyze it by inference line method, which you have read in structural analysis, right? You can use a quantitative approach, you can use a qualitative approach, either one that suits you. The second type of loading is the tandem design. The tandem design is a simple one in which two loads, equal loads of magnitude 24 kgs at 4 feet apart are applied on the bridge or girder or whatever the structure you want to provide, and it is analyzed for this type of load. And third one is design lane. So in design lane, the Astro design lane loading is like a caravan of trucks. It is 0.064 kip per square feet and is assumed to occupy a region of 10 feet. It is applied as 0.064 kip per square feet, which is, when you take it in pounds, is 64 pound per square feet of pressure to a width of 10 feet over the entire length of bridge for FEM. Okay, so just consider this bridge. This direction is the longitudinal direction in which the truck is moving or the tandem is moving, right? And this is the transverse direction or width of the bridge, right? So this is the bridge or which on which the lane load, the width of the lane is taken as 10 feet, and this 10 feet and this length of the bridge, for example this is 100 feet, so 10 into 100 is 1000 square feet area of bridge, and on this 1000 square feet the load of 0.064 kip per square feet is applied. So in order to calculate the area of the load of entire strip, you just multiply it with 1000, so you will get 64 kip of load applied on this area, right? And if you want to transfer it into unit feet of strip 1 feet, so you just multiply this with the 10 and you will get 0.64 kip per feet. See, over here it's per square feet, but when you just apply it linearly and you take 1 feet width, then you have to multiply it with the 10, and this is what you get in a per feet, in a running feet form. Okay, this is in a square feet form. So in summary, it says that three design loads should be considered: the design truck, design tandem, and the design lane. These loads are superimposed in two ways to yield the live load effects, which are combined with the other load effects. The two ways of superposition are: number one, if you combine truck plus lane loads, means that you applied a 0.64 kip per feet and you add the HL93, or the second one, you applied the tandem load and the lane load simultaneously. So you analyze for this case and you analyze for this case, and the result of both analysis you compared and the maximum bending moment you get when you have to go for the design for that bending moment. So it could be truck plus lane or tandem plus lane. Okay, now coming to the load modifier, a factor accounting for ductility, redundancy, and the operational importance of the bridge. It is taken as 1.05 for simply supported bridges and is applied on already factored values of bending moments. Okay, so once you get the mm, factored bending moment, you multiply it with 1.05 for simply supported bridges to and to account for what, the ductility and redundancy, okay, and the operational importance of the bridge. So it is just extra care and extra caution you are taking in terms of bridge importance. That's it. So, uh, after discussing all the basic uh, terminologies and the basic parameters, now we are able to go for analysis and design of the simply supported RC slab bridges. So, let me tell you clearly that the bridges, uh, it is not that simple, and we are just considering a very simple case because at this level we can only understand this kind of analysis and design of a bridge. The bridges can be the T-beam bridge, the bridge can be I-shaped girder bridge or the box girder, and these are the bridges I'm talking about, the RC bridges or the precast bridges we can construct. Okay, I'm not talking about the cable stayed bridges or suspension bridges. Their design is much more complicated and different design terminologies are involved. So we are just taking a very simple case of a slab bridge that its analysis and design will be performed here. So simply supported RC slab bridge. This type of bridge consists of only a slab without any other supporting members such as girders or beams or anything else. Okay, so just a slab is there and it is resisting all the loads. This is transferring the loads directly to the abutments or the supports. A slab bridge is widely used when the bridge crosses a minor road or small river. So if the span length is not that much long, so you can simply provide a slab bridge. And yeah, an example of this is, for example, when you are going on a ring road and you entered the Hayatabad. So the bridge that is provided on the phase 3 road as soon as you enter the Hayatabad, that bridge is slab bridge. There could be many more examples you will see in your everyday life. Okay, so now coming to the design lane in slab bridges can be analyzed as 3D, 2D, and 1D models. Okay, so of course 3D model analysis will be much more accurate as compared to 1D model, but in the same time the analysis of 3D will be much more difficult than 1D models. So 1D models will be much simpler, but the results will not be that much accurate. So if it is to be analyzed as 1D model, which is line analysis, the bridge width will be divided into various strips of unit width. These strips with a strip width of E are called design lanes. So you can divide it into unit feet or you can divide it into C, the design lanes. So the exterior lane will have a different width, however the interior lanes will have a different width. Right? Now the design lanes are then transformed to line elements, which is 1D model for line analysis. The moments are calculated from line analysis. These moments M are then divided by the design lane width E to get moment per feet for the slab. Okay, so when you are taking a strip, for example, the interior strip, the design strip, right? And you are just transforming the design lane into one line, and for example the width of the line is 1 feet, and you analyze it and you calculate the bending moment. Now you divide that bending moment m on the design lane width, okay, the initial lane width that you got. So over here you can see that. Okay, let me tell you first that this was the width E of exterior lane and this was the width E of interior lane. You just transform this interior lane into this line strip of unit width. You calculated bending moment for this and then you divided this bending moment on the width of this strip. So you get this, that more M divided by E, moment divided by the lane width. Okay. So design lane widths can be calculated using equations given as follows. We will see on the next slide. But let me show you this thing as well. This is a simply supported bridge. The truck is moving in this direction. You see the 8 caps and the 32 cap loads are applied. So the maximum bending moment is right over here under this point. So this M, you will divide this M over E, so you will get moment for the design lane width. Okay, this is the procedure, but we will discuss in detail, don't worry at this point. Now, as we discussed about the design lane width, which is different for exterior lane and for interior lanes. So coming for a case where a single lane is loaded, and you can see in the figure that there is only one truck moving on the bridge. Only one lane out of three lanes is loaded with the truck, right? So in this case, E, and remember that the units are inches. E is equal to 10 plus 5 under the root L1 into W1. Now what is L1 and W1? It explains that L1 is a modified span length which is minimum of S and 60 feet. What is S? You can see from the figure that this is the longitudinal length. So if S is greater than 60, so you have to take 60. If S is less than 60, you have to take S. Okay, so you will get L1 in that case, whereas W1 is the width, as you can see from the figure. However, what width? It is modified edge to edge width, right? You have to include the barrier width as well. Minimum of overall width of bridge W1 or 30 feet. So whichever is less, you have to take that width, that value. So L1 and W1. L1 is the length, the modified span length, and W1 is the modified width of the slab bridge. And the next case is, as we all know, that for a multi-lane loaded. So in previous figure, we saw that there was only one truck present in a single lane. Now what if more than one truck is present simultaneously on the bridge at the same time? So in that case, the E, which is the width of the design lane, E will be equal to 84 plus 1.44 into under root L1 W1. We know what is L1, we know what is W1, and this value should be less than or equal to W1 divided by NL. Now what are these new terminologies? So L1 as same as single lane loaded case, which is minimum of S and 60 feet. W1 is minimum of overall width of bridge or 60 feet. In previous case, it was minimum of 30 feet or width of bridge, right? If you remember, over here it's double. What is NL? NL is the number of design lanes, and it is the integral of W divided by 12. Design lane width E is the smallest value of 1 and 2. So you will analyze it for a single lane loaded and you will analyze it for multi-lane loaded. So equation 1 and 2 will give you two different values, and the smallest value of both of them will cover, and you will take it as the design lane width. Okay. Now after deciding the width of the design lane, we will come to design of RC slab bridge. The depth h will be equal to 1.2 into s. You know the s, it is the length of the bridge plus 10 divided by 30. S is the span of the bridge. See, the length of the bridge or the span of the bridge. Now, as we know the general capacity and demand equation, that the demand should always be less than or equal to the capacity, okay, of the structure. Now mu, which is the demand, is equal to 1.05. If you remember 1.05, this is for the bridges, the ductility and the redundancy factor, into 1.25 mdc. If you remember, for the structural and non-structural dead load, the factor was 1.25, and for the wearing course, the factor was 1.5, right? So we have seen all these things previously, and 1.75 m live load. Okay, so in live load, we have discussed the vehicular loads, if you remember. So this will give you mu per feet, right? Now mdc is equal to, in this one, wdc s squared divided by 8. What is wdc? Wdc is simply the unit weight of concrete into thickness of the slab, or h of the slab, right? What is MDW? It's the same equation, whereas you have to use the unit weight of wearing surface. Live load moment is equal to, as we discussed previously, that M tandem or M truck, whichever is greater, you have to add it with the lane moment, okay? And it will give you the live load moment. Convert M live load to fit kip per fit, divide M live load by E design lane width, okay, as we discussed previously. So it will give you MLL, the live load moment. So this is how you have to perform the analysis and calculating the bending moments. Now, discussing the live load moment in some detail, the slab moments due to live load. Moment due to HL93 truck load, M truck. Maximum moment due to truck load can be obtained by placing the middle axle, which is this one, at center or mid-span of the bridge, and rear axle at a distance of 14 feet from the middle axle. So as we know that this distance is fixed by ASHTO, it is 14 feet, but this distance varies depending upon different requirements. Usually they take it from 14 to 32 feet, but they said that if you are making it as 14 feet and putting this point at the middle, so it will give you the maximum bending moment at at this point, okay? So after truck load, there is a tandem load, which is M tandem. Maximum moment due to tandem load can be obtained by placing the two loads at a distance of 2 feet from the midspan. So this is midspan, the center of the bridge. You put both the loads at 2 feet from this point, as you know that the distance between both the loads is 4 feet. So in this case, you will get the maximum bending moment. Okay? And the third one is, we know that design lane. And as we discussed previously, the moment due to design lane load ML M lane is equal to 0.64 into which is W, that's square divided by 8. So in that way you will get the design lane load. So you combine this load with the tandem or with the truck, and whichever gives you the maximum moment, you take it as a design moment. So after getting the maximum moment, you go to the design and distribution reinforcement and bottom transverse reinforcement. ECI A5-1441. It says that area of transverse reinforcement is equal to, the transverse area is equal to 100 divided by 100 S, or 50% of area of steel, whichever is less, but it should not be less than shrinkage reinforcement area, okay? So AST minimum of shrinkage is equal to 0.0018 of gross area. The shrinkage and temperature reinforcement in top face of slab, longitudinal and transverse both for grade 60 steel is 0.0018 into Ag, and it is different for the grade 40 steel, okay? Now reinforcement detail in slab bridge. This is the slab bridge, and if you take a section in this direction, so this is what you will see. The width of the slab or the transverse direction is this, and the longitudinal direction is the one perpendicular to the screen. As per shrinkage and temperature reinforcement requirement, you have to provide the top bars in both the directions, in longitudinal as well as transverse direction. However, at the bottom, the longitudinal bars are the main reinforcement to be designed. As we saw that the bending moment, maximum bending moment is in the direction of the movement of the truck, so which it is this direction. So main bars are these bars. However, the bars in the transverse direction at bottom are the one we were talking about, that it should be least of 100 divided by 100 S, or 50% of this main bar.